Welcome back to section 7.3, the eigenvalue method for solving systems of linear differential equations. We're going to focus on the first order ones. So as a quick review, we had our differential equation, system of differential equations that led us to a matrix. We found the eigenvalues and eigenvectors, and that led us to find then the solution to that system. So now it's your turn. Let's go ahead and have you try this one right here. So use the eigenvalue method for finding the solution to this system of differential equations. And we'll even make up some initial conditions. I used my calculator to randomly generate some numbers between -5 and 5, and I got 1 and -3. You can choose your own if you'd like. But we'll pause there, let you work on it, and then we'll come back together and see what you got. So let's come back and compare notes. So I took and wrote out the system from which I noticed that it could be a matrix equation, and where the matrix is 4, 1, 6, -1, the coefficients. I then move over to find the eigenvalues and eigenvectors by doing ax equals lambda x, solving that. So a minus lambda I times x equals the 0 vector. So taking the determinant of this, setting it equal to 0, we find out that our eigenvalues are 5 and -2. For the eigenvalue of 5, we find out that the corresponding eigenvector is 1, 1. So the x1 vector solution is 1e to the 5t, 1e to the 5t. For the other eigenvalue of lambda equals -2, we solve and get that the eigenvector is -1, 6. Therefore, the x2 vector solution is -1e to the -2t and 6e to the -2t. Therefore, we can combine and create a linear combination of those guys. And if we do so, we get this guy right here, which we can interpret this way. Okay. Because if these vectors are equal, then we can add the like components. Recalling our initial conditions that x sub 1 is 0 and x sub 2 at 0 is -3, we find out that C2 is -4/7, and then knowing that, we find out that C1 is 3/7. Plugging those guys in, we get this guy right here. And just by way of check, just to make sure I didn't make any silly mistakes, I looked back here and said, hey, what's x1 prime? Well, it's 4x1 plus x2. So if I take x1, which would be this first line here, and I do his derivative, I get this. If I do, and I remember that x1 prime is 4x1 plus x2, if I do 4x1 of t plus x2 of t, I get 15/7 e to the 5t minus 8/7 e to the -2t, which is in fact x1 prime. So I'm pretty confident I didn't make any silly mistakes. All right. Next up, let's review some work that we learned in section 5.3. So there we were able to solve differential equations that were second order with constant coefficients and linear. And if that's true, then we expect the solution to be y equals e to the rt. Let me switch pens on that. E to the rt, that is. Therefore, that leads us to the characteristic equation r squared minus 6r plus 25 equals 0. And we could complete the square. So I'm going to do two baby steps in one. So r squared minus 6r, and then I'm going to bring that to 25. I'm going to subtract 25 from both sides, so we have minus 25 over here. And I'll complete the square by taking half of the linear term and then squaring it, which is adding 9. And if I add 9 over here, then we find out that we have a perfect square. R minus 3 quantity squared equals -16. And if we take the square roots of both sides, we're going to get r minus 3 is equal to plus or minus the square root of negative 16, which turns out to be plus or minus 4i. And therefore, r is, adding 3 to all sides, 3 plus or minus 4i. Now remember, the reason we did that was to find the solution, and our solution was y equals e to the rt. We now know what r is, so y equals e to the 3 plus or minus 4i t, which we could write as e to the 3t times e to the plus or minus 4it. But we saw in chapter 5 that these are complex conjugates here. So if we use Euler's formula, we can get our two linearly independent solutions from using just one or the other. So we would get e to the 3t times cosine of 4t plus I sine of 4t using Euler's identity. But we then said, hey, let's throw in some constants there. So we'll throw in a constant 1 here and a constant 2 there that might absorb the i's, and these don't have to be real constants, they can be complex. Therefore, here is our general solution to our differential equation. If we wanted to, we could break them off into pieces where y1 was equal to c1 e to the 3t cosine of 4t, and y2 is equal to c2 e to the 3t sine of 4t. And you can use your Wronskian to check that those are in fact linearly independent solutions. Next up, before we go to our final problem for the section, I want to have you review some complex number arithmetic. So solve these arithmetic problems with complex numbers, and then we'll come back together and see what you did. Okay, we're back. So hopefully you remember that to add complex numbers, we add the corresponding real parts and add the corresponding imaginary parts. Similarly, for subtraction, we subtract the corresponding parts. Multiplication, we need to remember to use our distributive law. Okay, and the fact that a times b and b times a, those are real numbers, so they subtract out. And remembering that I is the square root of -1, so I squared is -1 times the negative here makes that be a squared plus b squared. And the important thing to note here is when we take a complex number and multiply by his complex conjugate, we get a real number always. And that's important because that's actually how we did division for complex numbers. So if I do -5 plus 2i over 4 minus 3i, I'm going to write it in this format, and then I'm going to times by 1, and that 1 will be the denominator's conjugate, top and bottom, so that he's really just worth 1. The reason for doing that is the bottom now turns into a real number. I will have to do some multiplication on the top, but then I could simply break up that fraction to get his answer. So here's our complex number answer to the division of two complex numbers. So we'll stop there and pick up on our next problem in the next video.